Welcome. My name is Craig Buchek, and I'm going to talk about HTTP today. So this is about a half an hour of slide presentation, and then probably an hour plus of a hands-on workshop. So that's working. All right. You can tweet me at Craig Buchek. You can hit me up on GitHub at Booch, where my presentation is. If you go to Booch, GitHub/Booch/presentations. The workshop actually source is now at GitHub Booch. I think it's called HTTP Workshop. I've got projects there. Sort of my side business stuff, or you can email me there at that address. And I'll have those at the end. You can actually follow along with the slides if you want to on your laptops there. HTTP Workshop, boochtech.com/slides. And actually, when we get to the workshop, you'll have to go look at those slides to follow along. So about me, I've been doing Ruby on Rails since 2006. Apparently half my t-shirts are Rails Conference t-shirts. Before that, I did network admin, system admin. I was a firewall admin, so a little bit of security. I don't like to talk about that because I'm not very good at it anymore. I've been doing HTML since about 1995. Pretty much just amateur at that point. I guess about 94, 95, everyone was an amateur at it. And I'm a boring slide designer, so black and white slides, sorry. There's a little bit of color, but only where necessary. So we'll talk about HTTP basics, requests, the different methods, responses, proxies, troubleshooting, HTTP version 2, and then we'll get into the exercises. So HTTP came about in 1991, and then it was standardized in 1996 with version 1. Version 0.9 is sort of like a retroactively given version number. There's not actually a version 0.9. In 2007, if you notice there's a big gap between 1996 and 2007, HTTP version 1 came out. Some updates to that. The RFCs, they basically just rewrote them, clarified them, and broke them into bigger pieces so that they were in preparation for HTTP version 2, which came out in 2015. So again, 8 years between there is quite a long time that not very much happened. But version 2, we'll see a lot happen actually. So the basics of HTTP. HTTP is a stateless protocol, which means that you make a request, you get an answer back, and that's it. So it doesn't keep a state between one call and another, except one little trick called the cookie, which we'll get into later. It's text-based until version 2, which means that it's very easy to look at, to do these exercises, to use a protocol analyzer on the network to watch traffic go by. It's easy for humans to work with. And I talked about a request response. Your browser makes a request to the server, and the server sends a response. So generally just that one request and response cycle. So when you make an HTTP request, you request what's called a URL, Universal Resource Locator, also a URI, Universal Resource Identifier. There's a very, very subtle distinction between those two, but for all practical purposes, they're the same thing. So we've got different parts here. The first is called the scheme. Most of us call that the protocol. Usually it's going to be HTTP or HTTPS. The versions of that aren't going to be in your URL, but they will be in the communication channel. The next part is, that big part is the authority, which includes the host, which is the server you're going to hit, the port you're going to hit it on, which is usually you're just going to accept the default. So most of these pieces you don't need to specify. They have defaults. And then the user info, which is a username and password. You'll rarely see those inside of a URL anymore. Usually now you'll get a pop-up instead, or you'll get logins inside of the browser, which actually are two very different mechanisms. Then you've got the path. So basically everything after the server name and or port, here is /abc/index.php is the path. So that is a file on the web server that may be, well, originally it was a file on the web server until we got applications, so it might not be anymore. After that, there's a question mark with something called a query string, which is usually how you would pass in like a search. Like if you go to Google and you type in something in the Google search bar, and then you look up at your URL bar, it'll usually have Q equals and then what you typed in. And those are separated by ampersands, so there's a name, a value there. And then a fragment, which is starts with the hash mark sign. And that basically tells the browser where within the page to scroll to. Although that has been abused by Twitter for a long time to do some other things, but that's the way it's supposed to work. Let's see, I got it. All right, so this is what an HTTP request looks like. We'll be seeing more of this for sure. So I color-coded these to highlight the various parts. So the first part is the method. So this text actually here, before the bullet points, is actually what a browser might send to a web server. That's the request. So the first part is a method. We'll get into what the different methods are. It's basically saying I want to get something or I want to change something, various variations of that. The next is the URL path, which might be a full URL or it might be relative to the server, depending on which version of HTTP. Then unhighlighted there is the version of HTTP for this request. And then the next set is a set of headers. So these would be request headers in the request. Here you've got a host header and a content link header. And then you've got the body. And we'll talk about each of those a little bit more in some detail. So the HTTP methods are get. These are the most common methods that you're going to see. There are some others. So get, which is 90% of all web traffic, is probably a get. So when you go to http www.google.com, you're going to do a get request. A post is when you're submitting something. So when you type in something in the Google page and you hit enter, that would be a post. A put is when you're trying to change something. Actually, it's more of an upsert. So you can theoretically create something with a put, but I've never seen it happen. There's some difficulties in that. You can actually delete resources, pages, things inside of pages, things inside of apps more likely. And you can do a head, which basically is the same as a get, but it doesn't include the body when you get that response back. Since I don't have my presenter notes, I'm going to peek over here at those. Okay, there's a few other methods. There's trace, option, and connect. There's some more extensions called patch, and there's something called webdev, which extends some of these to do things like make directories and such. Let's see. Oh, sometimes the methods are called verbs. You notice those are all actually verbs except for head there. And if you're going through some sort of firewall, you might not be able to actually, or proxy, you might not be able to do some of these. The one that's probably most likely to not work would probably be the put. And there's some workarounds for that. So methods have a concept of safe, and these are in the RFCs. The RFCs are requests for comments that the Internet Engineering Task Force puts out, which are basically the standards for running the Internet and the web. So one of the things specified in the RFCs is methods that are safe. So this means that they don't have any effect on information. So if you run these, they won't change the state of the server in any way. So get is pretty much the main safe method. So So if you're not safe, you're unsafe, right? So you're going to be changing things. So the things not listed here, like post and put and delete, are going to make changes to things on the server, assuming they're accepted. So idempotent methods, I've heard that word pronounced idempotent or idempotent, or a couple different ways. I think idempotent is the way I've heard it most. So idempotent means you can do the same function multiple times and get the same result. So if you get google.com, you're going to get the same thing every time, unless they make some changes. If you do a put, if you say, hey, change the thing to this, this is the same, so you're always going to change it to the same thing. And if you delete something, it's going to be deleted when you're done, even if you try to delete it multiple times, right? So those are idempotent methods. Note that post is not, and post is the thing that we do the most. Post is usually used for creating something. And so a lot of times you'll see the button that you hit to post something, to save something, or in a create page. Sometimes they'll ghost that out so you can't hit it twice so that you don't accidentally create two things.
So you're saying that put is kind of like an upsert?
Yeah, it is actually an upsert, but everyone uses it in an update instead of an insert. So effectively, it's an update.
But if you were to try to use this insert, you get the benefits of idempotency?
Yes, the problem is that you don't know yet where URL you should put to. Yeah, that's the issue. So request headers. So the most common request headers you're going to see, the host header is required in almost all cases, except for an older version. Actually, I should probably tell what each of these things is. So the host header, let's say you're Google and you've got google.com and you've got alphabet.com. And you've got them both on the same server. So when you connect to that server, it doesn't know which one you're connecting because it just, the name got converted to an IP address, you connect to that IP address, and at that point it's lost that information. So the host header puts that information back. It either says host www.google.com or host www.alphabet.com. And that lets you have multiple web server hosted on the same server. The accept header says basically what type of files the browser is willing to accept, willing to show. So let's say you've got a new version of Chrome and it can handle XML files in addition to HTML. It would put XML in the accept header. Content length. So most of the time you're doing a get, but if you're doing a post or a put, you're going to include the body. The length of that body in bytes goes into the content length. Again, if you have a body, the content type. If you're working with an API, you might be posting XML or JSON, so you have to tell it which one of those it is with the content type. Refer is spelled wrong, by the way, but it's spelled wrong in the standard, so we still use it spelled wrong. So the refer is if you're on a browser and you click a link from one site to another, the original site's URL gets put in the refer header when you go to the new page. So websites can see where people are redirecting to their website. The user agent string is the version of the browser. We will see that a lot in the exercises. Peek my notes. Let's see. Oh, hey, that's what I have to say. So if you're playing along, there's some more details in there that are probably not worth mentioning. Excuse me. Let's see. The authorization header is for the pop-up authentication when you're, most websites don't have the pop-up, but if it has a pop-up that's done by the browser, that's using the authorization header. Accept encoding, I believe, is if the browser says, hey, you can zip this up and send it to me compressed so we can save bandwidth across the internet. We don't have to send, let's say you've got 100K of JavaScript. If you gzip that up, it's probably even down to probably 12K or so. So encodings are pretty cool. Connection. In version 1.1, I talked about how you make a request, you get a response. That's the end. connection, you can say keep alive, saying, hey, I actually have more than one thing to get from you at the same time. So let's not have to tear down and rebuild the TCP connection to get that.
Is that similar to or the same as what socket connections do, like socket
I mean, it does make a socket connection down at the TCP layer. So it basically just keeps that socket open. Or the, yeah, outbound socket. So a cookie, remember, you can see if, all right. All right, so the cookie is the way to do, so we take a stateless protocol and we get state, like the state of being logged in to a web page, a web app. The way that works is the server will give you this cookie. It's just a token, a string of semi-random characters, and the server will remember who it gave that token to and keep the state in a database or some other thing associated with that cookie. And so the next time the browser makes a connection, it passes that cookie back in the request. And the server then is able to look at the cookie and say, oh yeah, hey, I saved state for him. Pull that state back up. Now we've got statefulness. All right, the HTTP response. So it starts with the version of HTTP we've got, and then it has a status code. And it's got a string for the status code, but the status code is actually what matters. I think I've seen some slight variations in the actual string there after the code. So I don't think anyone really looks very carefully at the string, but just the code. So we've got response headers that look a lot like the request headers. And we got a body, which usually you're going to see a body in the response. Not 100% of the time. Like if you're deleting something, you probably won't see it. If you're creating something, actually, you might not see it. It might just give you a header saying, hey, I created this. Here's the URL. Go look at it. My team has actually been having an argument. Should we pass the data or should we just pass that link? The weird thing is that the users just passed almost all that data except for probably the ID or something like that, or some defaults that got set. So the body, if you go to google.com, it's probably going to be HTML. In this case, got some JSON there. So that response code, it's the status code. There's various different divisions, and they're all well-defined. They're all in standards. Any response code you get back should be in a standard, hopefully. So 100s, I don't think I've ever seen that in practice except for HTTP 2. There's a little piece that sort of upgrades from HTTP 1.1 to 2, which looks really weird. 200 is probably what you're most familiar with. Well, maybe 404, which is on the next page. So 200 is if you do get, and it says, hey, the page is here. Here's the page. You'll get a 200. Okay. If you're doing a post, possibly a put, and everything works out, you'll get a 201. I think there's a 204. I didn't put notes on that. I've seen a 204. I think I've had an API that handed out a 204. I think a 204 is no content. I think that's what you get when you do a delete. Redirection. So we have an exercise on redirection. So there's a couple different ones. Move permanently is usually what you'll see. Actually, a good example is if you go to google.com without the www, you'll get a move permanently, and it'll send you to www.google.com. There is a good article that has a good reason for using www.google.com instead of just plain google.com, which is why Google does it that way, even though it takes a little bit of extra bandwidth to do that. Not modified. We have an exercise on that one too. So basically, the browser can say, hey, you sent me this page like yesterday. Has it updated or not since I got it yesterday? If not, just tell me it's not been updated, and that's what a 304 is. And we'll have an exercise showing that. So here's the bad one. So all these were pretty much 100s, 200s, 300s. They're pretty much success codes. These are pretty much failure codes. So 404 is the one you see most often of these. Page just isn't found. Unauthorized would be telling the browser to pop up that authentication panel. 403 is if you've authenticated, but the web server says, hey, you can't get there, but this exists, which is a bit of a security issue to even let someone know that something they can't get to exists. So sometimes they'll just give you 404. So like you can get the unauthorized to pop up a panel for the website, Proxies can actually send a 407 to make you authenticate to the proxy. We do have an exercise I just added late this afternoon using a proxy, but no auth. I didn't think about that one. The one I tend to use most for an API is 422, which basically says, hey, this is well-formed XML or well-formed JSON, but hey, I require you to have this field and you didn't include it. So 422 is usually the best option for that. A lot of times, developers will punt and just call it a plain 400 error. 500 errors. 500 is pretty common where just the server crashes or something, the application crashes. Bad gateway, we might get to do that exercise. Basically, it says that a proxy can't find the server behind the proxy, which is actually called the origin server, even though it doesn't originate anything. Go figure. And 504 is basically the same thing, except that the backend web server exists. It just didn't respond within like 30 seconds or whatever the proxy is set to timeout. I know I have some notes on this one. So there's actually, April 1st, the standards groups actually put out some funny RFCs. So there's actually a 418, I'm a teapot. And there's, oh, actually this is a real one, 451, and unavailable for legal reasons. Anyone know what 451 is significant? Fahrenheit 451, 451. So pretty out there. And there's method not allowed. So basically, if an API you are trying to do a put and it doesn't allow a put, you continue a 405. So there's a couple pages. Again, these slides are online. Don't have to copy these down probably. So some references to get more info on status codes. The Wikipedia page, as usual, is pretty thorough. And pretty good information. I believe that last one, let's see. Yeah, the last one is the IANA, which is the Internet Association of Number Assignments or something like that. So basically, if there's numbers in something, they're the ones to go find the authoritative list. So that last one is the authoritative list of status codes. The first one, http://statuses.com, is sort of a little friendly page. Has some friendly info and tells you like what constant to use in Rails and Go and such. All right, response headers. So just like we have request headers, we have response headers. Content length, this is actually the same thing as in the request. It's the byte size of the body. There's a content type, so typically you're going to see text/HTML. It's the MIME type, which again, IANA has a big long list. Content encoding is that the gzip. Did I gzip this? Did I? There's deflate. There's a new one I found like last week called Broadly that I think Chrome supports, and there's an Nginx plugin that I didn't want to compile, so I didn't make it work. Content disposition is an interesting one. Basically, if you want the browser to have the user save it instead of show it, you use content disposition. I forget the exact way to do it, but you can also specify a suggested file name for the browser to save as. Location is used for those redirects. So the redirect would have a location header and the URL that you are being sent to. Set cookie is that part I talked about, cookies for saving state. This is the server telling the browser to, next time it makes a request, send this little token back to me. www authenticate is that authentication pop-up piece. It says how to send the results back, and it says the name to put in the pop-up. Let's see if I have anything there. Nope. All right. Okay. Oh, I only had one page of response. All right. So a proxy, the word proxy means means something that acts in place of another. A web proxy intercepts your HTTP request, sends it on to something else, gets a response back for that, and sends a request back, or sends a response back. So because it sits in between, it can do several things. It can modify the request, it can modify the response, it can modify the headers, or it can even modify the content, although that's a bit high CPU load to change a big, long HTML page probably. I'm not saying it hasn't been done, because it is done sometimes. In fact, some of the ISPs, before we had net neutrality, and probably soon now that we don't have it anymore, will add a little add to your HTML. I think I got more proxies. All right, so proxies are good for caching. Let's say that you have a big company. Let's say its initials are AB or something, and you have a lot of employees in the building. And a lot of them go to google.com, you've noticed. So you're like, man, we're spending a lot on bandwidth, just go to google.com. Maybe we could, first time someone goes to google.com, cache it on our servers so that the next person that goes to google.com can just reuse that copy of the files instead of us going to go out there. You can add security. Actually, I did this a couple times where you've got a website and it doesn't know anything about users or logins, but you want to add some security with users and logins. You can have a proxy do that and not allow anyone to get past the proxy until they authenticate to the proxy. I've also done SSL termination. Actually, the setup for the workshop, Nginx is doing SSL termination. And the application server that I wrote in Rails doesn't have to worry about SSL and certificates and all that stuff. Authentication. So transparent versus non-transparent. So a transparent proxy is one that you and the browser don't need to know about. It's sort of in the flow of the traffic. A non-transparent proxy, which we'll have an exercise on, is one that you have to tell the browser, or your company forces the browser to have this setting that says, hey, anytime I make a request to the internet, go through this proxy, and it'll actually make the request. So maybe that caching might be either transparent or non-transparent. One advantage of a non-transparent proxy is it can actually do HTTPS requests for you. Actually, it's a disadvantage depending on how you look at things. Reverse proxies versus forward proxies. A reverse proxy is a proxy that is near the server and run by the same people or run for the same people that run the server. Actually, in my exercises, I have a reverse proxy that you connect to. I'll put the URLs in this. But the URL we'll go to is actually the reverse proxy, and it knows to go ask the Rails server. A forward proxy is one that's closer to the browser. So usually a non-transparent proxy is going to be a forward proxy. And a reverse proxy is always transparent as far as I know. Something I added today, I don't know why this page is open, but the Charles proxy page is open for me. And I'm like, oh yeah, I forgot, proxies can be used for troubleshooting. So what this proxy does is, and actually all these pretty much work the same way except for the last one. So you set your proxy settings in your browser to point at this program running on your computer, and you make your web browser request or run your API, and these proxies actually record everything that went through, the request and the response. So you can actually look at them, all those requests and responses, see what's going on there. Really good for troubleshooting. The other thing that you can do pretty much the same way is the developer tools in Chrome and Firefox. Actually, Edge, I think, as well, and maybe in Safari. The last one is kind of interesting. It's called Slowy, and it slows down your requests and your responses to see if your JavaScript's going to break because it didn't get an answer fast enough. So while we usually have pretty fast internet, maybe you're using it in a country that doesn't have fast internet, and you need to see how it performs. When was it? It was last week. I saw, I don't remember what company it was. It was like Facebook or Google, or I think it was Apple. It said that basically all their developers work in Cupertino, and they have fast internet. So if you've got slow internet problems that are causing a bug in the software, they can't reproduce it because they have fast internet. Chrome has a slowdown. Nice. Nice. I did not know that. That's good to know. So in case that didn't hit the speaker, Chrome has a feature where you can tell it you're on 3G to slow down your requests and responses in the developer tools. A CDN, a content delivery network, is basically a reverse proxy run by a different company to cache static content. So if you go to google.com, the thing that you type in and go ask a response like, go look this up, that's not static content, that's dynamic content because you're getting different things back depending on what you type. But the front page, the graphics, the icons are static content. They're always going to be the same. So Google pretty much has its own CDN, but other companies would go to, I think, Cloudflare or Akamai and pay them to host that content because they're able to do it probably cheaper. They've got servers distributed across the world. So instead of my small company having to get servers all across the world to make fast access for people across the world, I can just pay these people to do that. So in fact, some of these places will actually have, let's see, we have Charter and Uverse here, so that'll actually place a server, a caching reverse proxy, where I said it's closer to the server. It might actually be closer to the browser because that'll help you, right? So they might place it at Charter and Uverse centers in St. Louis so that we get faster access. So there's something called BGP Anycast, which determines which content server is closest to you when you do a DNS lookup. That's about the extent of my knowledge in that, so don't ask. DDoS protection, denial of service protection. So this is actually the company I'm working at now, F5 does. We provide a service that does DDoS protection. So if you are a big company like, let's say, Target.com, you can hire us and we will make sure that anyone attacking your websites actually attacks our servers instead of your servers. Target is asking for it. That's not actually a client because I figured I better not say who our clients are.
Quick question. So your definition of reverse versus forward proxy is super helpful for me as far as being closer to the server, closer to the browser.
Until I muddied the waters.
Yeah. Well, at
Yeah.
the very least, I was able to create reverse proxies for another app, and it makes sense that it's on the server because the client is sitting domain name, and then the
Yes.
reverse proxy is forwarding it on to the
Yeah.
server. Why is it called reverse proxies? Because that food is so hard when trying to figure out that.
Why is it called a reverse proxy? I can't actually explain that. Yeah, I guess it's from your point of view. Yeah, I'm not really sure.
I think Proxy would be another resource. I guess the first Proxy.
So I think the thought is that the first proxies were acting for me, the client, right? And that's actually acting on behalf of the server instead of the client. I think that's probably the point there. All right, so troubleshooting. We're called the full stack web developers, right? So the full stack includes the full stack of web. Hopefully some of you, probably not all of you, know about the OSI network layers. So when you're troubleshooting, think of those layers. Ping, can I ping it? Can I hit the IP address? Let's see, the OSI layers start from physical, data link layer, network layer, which would be the IP layer, and then next layer is transport, which would be TCP or UDP. So physical, we probably, I guess we check, hey, is the Wi-Fi working? That would be the physical layer and your link layer, sort of. But then the next layer that we can probably, unless you're a network admin, deal with is the network layer. So ping is the tool for that. Traceroute sort of is also a good tool for that. Next level up is the transport layer. We can use Telnet for that. We actually have an exercise or two on that. If you're on a server and you want to know, is my server actually listening for incoming connections? Nets tester tool. We have a exercise using that. If you're using HTTPS, which is your presentation layer, I think. OpenSSL S client as your tool. We've got an exercise on that. Back down layers, TCP dump, which actually can do a few different layers. Great for capturing packets. Great for looking at packets is Wireshark. You can actually use TCP dump to save a file and use Wireshark to look at it. One thing that Wireshark added way long time ago is actually taking all those packets and making them into a stream, so you can read it as just one long piece of text instead of a bunch of packets, so you have to figure out stuff. All right. HTTP version 2. Ask me 10 years ago. IP is the network layer. So, yeah, so it's not guaranteed. So TCP is connection. So the IP layer doesn't actually have connections. It just sends packets out. It routes packets. So TCP IP actually just routes packets at the IP layer. So you can send a packet out. If you're doing a ping, it actually sends a packet called an ICMP packet. Or if you're doing a trace route, and when it gets to the other end, it says, hey, I got this packet, I'm going to answer it. And there's just one packet back and forth. Same with trace route. So UDP is sort of similar in that it just sends a packet out. So it's not the best explanation of transport layer. TCP, transport control protocol? Okay. So what it does is establishes a session. So there's a three-way handshake, but I don't think that's important. So basically it recalls, okay, I've got this connection to this server on this port. And this port has been listening. Let's say it's port 80. Let's say we're making a web request. So my system with an IP address and a port, called an ephemeral port because it doesn't matter which port I use. No one has to find me except for that one guy. So I know I need to go to google.com. I look up his IP address in DNS to get a name to an IP address. So I send a TCP packet, which is wrapped inside of an IP packet. So IP knows how to get to that web server. I say port 80, so when it gets to that server, the TCP stack knows where to send it to in the computer. So that connection, when I make that connection to port 80, I have sent my TCP connection my port. He can respond back to my port and basically send the same packet. TCP layer keeps track of that connection so that these two can keep communicating back and forth. Unless the connection is broken somehow, a packet doesn't get one way or the other, that connection will stay up. And so I don't have to start over. I don't have to make that three-way handshake again. I can just keep sending packets through that connection, two-way connection.
Because TCP gets a response that goes to success, right? UDP doesn't.
Yeah, and it's even more complicated like that than that because that's the world of networking. It keeps track of all the packets it's sent and waits for a response to say, just a response that says, hey, I got that packet. And it's probably just tagged on along with the response packet. I make a request at the HTTP level and I get a response. So down at the TCP layer, there's packets going that way, there's packets going that way, and it's, if I send a request, it might be in 10 different packets. If I miss number 7, he says, hey, he sends responses and he's like, hey, you never sent me a response on 7. Here's 7 again. So that's what makes it stateful, that it's sort of guaranteed connectivity between the two.
So the networking transport layers work together.
Oh yeah.
The networking routes and transport
keeps that session together. All right. HTTP version 2 started as a Google project called Speedy. They were so fast at writing it down, they forgot some letters. I guess that's part of the joke. So HTTP version 2 has several features. One is header compression. So when I talked about that content encoding, I said you could gzip it or deflate it to compress it before we sent it over the wire. HPAC, that only happened with the body. HPAC allows this to happen with the headers as well. And sometimes the headers can be significant, especially if you're just sending really small API requests. The headers might actually be bigger than the API requests or even responses. Yeah, well, there's limits on how big a cookie can be, and I think I've run into it before. I think it's 4K or something like that. It might vary with different servers too. So even though the HTTP version 2 specification doesn't say you have to use TLS or SSL as it's previously known, every implementation I found uses TLS. It uses this trick to sort of promote from version 1.1 to version 2. I don't understand why. It uses this extension called ALPN, which is Application Layer Protocol Negotiation. There's a previous one called NPN, which there were some compatibility issues when I gave this for the first time in 2015, where I think the version of OpenSSL I used to build Nginx used NPN and Chrome used ALPN, and they wouldn't work together. Actually, I think it's Chrome, not Chrome.
The tricky part of that is that you want it to promote before data is sent over.
Yeah. Well, it's already secured. So the TLS layer, so HTTPS, which is HTTP with SSL, or now called TLS, that's already secure by the time you send any pieces of data, actually. So it doesn't actually have to do with that. There is a way to promote that using this, but I don't think that's common either. I think that might have been what SHTTP was. I think maybe. I don't know. There was something weird about that one that didn't catch on. Let's see. So binary framing instead of text-based. So when I said we could look at HTTP over the wire, HTTP 2 is kind of breaking that for us. We still have some tools that we're going to use in the workshop to still read it. The semantics are still the same. In other words, it's made into binary, but you can unbinary it back to the text. So you can still read it as HTTP 1.1 after you do that. But if you're watching packets over the wire, you're pretty much screwed unless you've got a tool to put them back together in the same way. There's a website at github.io called HTTP2. Let's see. Okay, more features. Multiplex connections. This is another thing that's going to make it difficult for packet sniffers. So multiplex means you can have multiple conversations going on in the same connection, which means we've kind of, remember the OSI layer? Well, let's throw it all in one place. Let's like, bad idea. But great idea, because now you can get, so if you're going to google.com, you need to get the HTML, you need to get the CSS, you need to get some images, you need to get some JavaScript. So that's at least 4 different files. In HTTP1, you generally had to wait for the first one to finish before you got the second one, or you had to make a second connection, which takes some time to build out that TCP handshake connection. So this multiplex, you can basically fire off google.com and like, hey, I know I need to get an image too. And the server can actually, with server push, the server can say, hey, you're going to need this image, you're going to need the CSS, you're going to need JavaScript. Go ahead, here, I'm going to start sending it to you before you even ask for it. I don't know what happens if it already has it. I think you can stop it, but I haven't looked into that yet. I wanted to do an exercise on that, but my version of Nginx isn't new enough to do that, and compiling it was a little more than I was ready for this week. So, in current practice, we usually like to take our JavaScript files and make one big JavaScript file, right? We like to take our CSS files and make one big CSS file. Sometimes we even take our images and do something called spriting, and we put a whole bunch of images on in one file, and we say, just grab this little piece here for this icon and grab this piece for this icon. HTTP2, you don't need to do that. So it kind of changes how we're going to build websites. Kind of important to know. Let's see. I already talked about how it upgrades the settings and the headers and your 101 status code. Only time I've ever seen that kind of thing. So I gave this in 2015, and things were just starting to support it. Some things didn't support it yet. Pretty much all browsers now support it. We're at what, Chrome 60-something, 70-something, Firefox 60 or 70. We're way past support for HTTP2. IE11, if you're on Windows 10 or newer, still newer, I don't know. Supports it. Edge, any version of Edge should support it, I think, and it's evergreen, so kind of version. Back in 2015, curl 4 was apparently the current version, and they had to specify the HTTP2 flag, and you had to make sure it was compiled in, and it was kind of a pain. Now you just, version 7.4.7 or newer, you're good to go. Wireshark 1.99, that's pretty old, supports it. Server side's a little more questionable. Nginx has of 1.9.5, they're on 1.15 now, but if you're running like CentOS 6, probably not. CentOS 7, I'm not even sure about that. Actually, I am somewhat sure that I believe you need CentOS 7.4. Apache 2.4.17, I don't know how long it's been out. They've got mod HTTP2. I believe it is included in Apache. I've pretty much moved all the Nginx now, so I'm not familiar with Apache too much anymore. HA proxy does not have support for it. It kind of does, so it's a proxy, so its connection from itself to the server will support HTTP2, but that's not the important side. You want it on the outside, and it does not support that. And they do not know when, because it's open source, and whenever someone submits it or gets around to it.
As far as HTTP2 becoming kind of just like the standard, is that point going to happen when I guess all browsers, all commonly used browsers support it, and all commonly used servers support it? Like, is that
Well, it can be negotiated with that last bullet point. So basically, you make an HTTP 1.1, and maybe this is sort of why it does it this way. I can make an HTTP 1.1 connection, and I can say, hey, if you support version 2, upgrade me. We're good to go. So you don't, I guess it's fully forward compatible. It's easy to get, you don't have the chicken and egg problem, I guess. But I mean, Nginx has it. Google has it. Most of the bigger sites have it now, I think. I didn't look too far into that, though. All the major browsers have it, though, so there's no reason for the servers not to have it. I know they had Speedy since 2012. It wasn't really ratified to 2015, so it couldn't technically have it, but effectively it had it. But mostly just to Google's own site. In fact, back then when the network's a little bit slower, you could almost tell because somehow it almost was like immediate. As soon as you hit enter, you got the answer back. You're like, what just happened? I think IE was doing something like that to Microsoft too, where it cheated, it didn't even wait for a TCP handshake or something really crazy. It was probably before the RC was even written down. Yeah. Yeah, that's one trick. It's somewhere I think it's in my presenter's notes. There's also a protocol called QUIC from Google, QUIC, which sort of takes the best parts of TCP and UDP, and so you can run HTTP2 on top of that. The problem with that is, I don't know if routers have to support it, or are they going to block it? I'm very curious about that. I have not looked into that at all. It's just some notes I found when I was investigating. So resources. You pulled these slides. There's an official site. I think that's the http2.github.io. There's a video you can look at, and the Nginx support was pretty handy for me. One of the
So, you said it changes the third-party sites, but right now you guys don't
yeah, that's kind of, now we're sort of in that transition stage where you don't want to slow down people using HTTP1 still. So you probably are still going to put all your JavaScript together. You probably can put all your CSS together. And you might not want to sprite your images anymore, maybe. I don't know. Depends. I mean, check your web logs, see what you're actually getting though. And maybe we're at the tipping point. Maybe you are, maybe I'm not. You have to look and see what you're actually doing. So one of the inspirations for this talk was a web post, an article called "What Happens When," and he talks about every step involved in showing a page in the browser, from entering the URL page, all the hardware, the operating system, the networking, really detailed and thorough, including like when you press the key on the keyboard, the electric signal and the interrupt that it sends to the operating system. Like, you went really thorough. But, hey, we're full stack web developers. This is part of your stack, right? In fact, all that, if you really were full stack, how does the CPU work? No one's really full stack. I'm close. Page with common HTTP headers. I don't remember if that was the Wikipedia page or some other page. All right, questions? Because we're going to get into exercise.